Okay. First of all, I would like to thank organizers for inviting me to this beautiful meeting. I'm going to present just in brief discussion of a particular problem in 1+1 directed polymers, which hopefully can be explained in 5 minutes.
Is it on?
I don't know.
Oh yes, so then put it closer.
Okay. Like this. That's fine like that. Okay. So directed polymer can be formulated if it's in continuum version. It's a function defined in the interval t. It's an elastic string to phi, which starts at 0, and at time t, it arrives somewhere here. It's an elastic string in a random surround, and so the energy of this stuff is composed of two contributions. Elastic term plus random potential, like this. And the random potential is considered as a Gaussian independent delta correlated stuff. So V of phi tau, V of phi prime tau prime average is some parameter strength of the disorder, tau minus tau pro, phi minus phi prime, like this. Then for this system, one defines the partition function in free energy. The partition function is defined like this. You integrate over all configurations of this string such that it's bounded to 0 at the beginning and it's equal to some x at the end with beta h of phi, this energy. Beta is inverse temperature. So the system is defined by two parameters, strength of disorder and the temperature. Then, of course, one can define the thing which is called the free energy, xt. And this, of course, both z and f, they are random quantities. And the whole story is about what is the statistics of these random quantities. Now, we know a lot of things about this system, almost everything. Not everything, but close to everything. First of all, in the limit, t goes to infinity, the free energy, random free energy, scales with the time like first term. It's a self-averaging, non-random quantity. It's something which it's not universal. It depends on beta u, proportional to time as it should be, proportional to the volume. Plus x squared over 2t. It's a trivial term just because of elasticity. If you imagine here a straight line, it gives this contribution. And finally, plus something much less trivial, u beta to power 2/3 t to power 1/3 times f. So this is non-universal coefficient, time to power 1/3, and this f is a quantity of the order 1, which is described by so-called Tracy-Widom distribution, which is highly non-trivial stuff, defined by the solution of the Panleve 2 differential equation. Anyway, it's a universal function which contains no parameters. It's a beautiful thing. It's non-symmetric. And this is just a coefficient. Then, during these last years, we managed to compute, for example, multi-point joint distribution of free energies. Then it's known, for example, that instead of fixing x here, you let you introduce integration so that the boundary will be free, then it will also be a distributed according to Tracy-Wheeler, but of the type, this one it's of the type GU. But if it's free, then it's JO, and so on and so on. Then we know, for example, analytic expression for the distribution of endpoint, and so on. The thing which remains unclear, it's a time statistics. It's much more complicated thing. But today, I'd like to propose one more direction in terms of this system, which is sufficiently simple in my view. So one may ask the following thing. Look, we have, for a given temperature, random f, well, it's a fluctuating quantity, and the distribution is known. There is a coefficient. If we change the temperature and look at another f at a different temperature, it will be also random quantity with the same universal distribution and changed coefficient. So not much difference. But one may ask more.
What's the distribution of x? What's the function of x?
This is the function of x and t.
Right, but little f.
This f, it's a random quantity, which is not a function, it's just a random quantity of the order of 1, which is described by universal distribution which have such a form. No parameters, it's just a random quantity of the order of 1. One may ask the following thing. If we consider the same sample and they fluctuate in f at 2 different temperatures, to what extent they are correlated? Separately, it looks the same, but it's clear that if the temperatures are very close, the random stuff will be highly correlated. If temperatures are different, maybe they are correlated, maybe not. That's in spin glasses, it's called the temperature chaos problem, and there it's much more complicated than here. Here, I pretend to say that it's more or less clear what's going on. So, more specifically, instead of introducing 2 points, 2f joint distribution function, I would like to introduce a difference of 2 free energies at different. Moreover, I introduce a quantity like this. For technical reasons, it's more convenient to consider this is a function of beta 1 minus beta 2 f of beta 2, or beta 2 like this, because this is xt and this is beta 1 xt, like this, the difference. And I would like to know this beta 1, beta 2, what is this stuff? It's done, it can be done in a rather simple way if we apply all the machinery of the replica technique. The standard trick, if we have something of that type, let's consider what this thing is, exponentiate of f. If you take exponent of that, we'll get e to the power minus beta 1 f1 times plus beta 2 f2, right? By definition, it's equal to z beta 1, z minus 1 beta 2. This is one partition function, this is another partition function, okay? It's a definition of free energy. Then we take nth power of this thing. On the right, we have z beta 1 to power n, z beta 2 to power minus n. Then we average over this order, both sides. Like this. And here we explicitly use averaging over P of f, which we look On the left with this, on the right we have that. If we know this quantity for arbitrary n, then we say magic words, we analytically continue to arbitrary n real, and then one can try to do inverse Laplace to recover this partition function. Anyway, one has to know this object to do something. This object is not very nice because we have denominator here, which is a traditional problem in these random systems. So, but traditional trick in replicas, we say that it is equal limit m to 0 of such thing n times z m minus n average. First we introduce integer m, which is larger than n average. We call this z, which is a function of m n into temperatures. We have to compute this for integer m n, then we have to take this limit to 0, and then maybe we can recover this p. Unlike that formulation, where originally, I mean, in the original problem, it has been done more or less in the same sense. You have on the left, you have the Laplace transform of the partition of the distribution function. On the right, you have a partition function, which in the original formulation, it was possible to compute exactly. Now here, this problem, at least I don't know how to do it for arbitrary beta 1, beta 2. But there is one more trick. If you do not pretend on an exact solution, you can find an asymptotic of the distribution function on the left asymptotic when f goes to minus infinity. And at the same time, it allows you to know scaling, which way this f scales with time. How much?
2 minutes.
Oh. Okay, so just in brief. So the trick here is this. I cannot compute it for arbitrary mn, but I know how to compute it in the limit when n goes to infinity. This will go to 0, but if this is considered to be large, on one hand, it defines left asymptotics, because if n is big, and this f is negative, this can be estimated by a saddle point with respect to p. On the other hand, if this n is large, in this problem, which can be formulated in terms of quantum bosons, one can use only the ground state solution, and that's enough. And then the result. The result is that this f scales like some function of beta 1, beta 2 to power 1/3, t to power 1/3. This function can be found explicitly. It's not that interesting. It's just a algebraic expression which takes such space, cumbersome. But what is interesting is that if we consider t1 minus t2 over t1 to small, so the two temperatures are close to each other, one finds that this scales like 2 to power 1/3, t to power 1/3. That's the main result. That there is one more 1/3 in this story. One can consider also limits when this goes to infinity, or everything is compatible. But this is one more 1/3 in this story. And in addition, one finds that p of f, when f goes to minus infinity, scales like exponent minus 2/3, sorry, this f, random quantity, f 3 over 2. So the left tail coincides with Tracy-Widom left tail, but it also coincides with just ordinary I function. So it doesn't tell anything about the body, but at least it gives the scaling. That's all.
Okay, thank you. have a question. This P of F, does it depend on tau, or it has a limit if tau is small?
This? No, 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 it's a universal function. You have a quantity big F, difference of two free energies. It scales with temperature and time like that, and it multiplied by on a random quantity which is described by universal distribution which does not depend on anything. This distribution is not known.
It's not known. It's not one of the Tracy-Williams.
Maybe, but no one knows.
Okay, thank you. Thank you.